Hi, I'm Professor Goings. In this video, I'm going to take a look at the special case of a certain type of function called a constant function and its corresponding derivative. Two things to remind you of. First of all, recall, what is the derivative value? Well, let's say I have this graph of a function f of x, and I pick a specific point on the graph that, say, corresponds to x equal to a. If I look at the corresponding point on the graph, and I draw the best linear approximation at that point, that's called the tangent line, and the slope of the tangent line is given by the derivative evaluated at that point. Also recall that a constant function, the graph of a constant function f of x equals c, where c is any fixed real number, is parallel to the x-axis. So it looks like it is basically the x-axis just shifted up or down. Now let's tie these two together. Let's pick a specific point, A, on the x-axis here. Let's look at the corresponding point on the graph of a constant function. And what is the best straight line approximation of a line? Well, it would be the line itself. This red line is the best straight line approximation of the blue line. What is the slope of the red line? The slope, which would be the value of the derivative. Well, the slope of the red line is 0 because it's a horizontal line. That must mean that the derivative value at that point is 0. But the a value was arbitrary. If I was to slide the a value over here, point on the graph would be here. Best straight line approximation would be a horizontal line. All the way along here. So let's make a guess that if a function is equal to c, then its derivative certainly seems to be 0. Let's verify that though. Let's look at the formal verification of that sort of educated guess. If I have a constant function, let's look at its corresponding derivative. And remember that the derivative is given by the limit of the difference quotient. Oops, over h, not over c, over h. All right, now for this particular function, f of x equal to c, the output is always c, no matter what the input is. So therefore, if I plug in x plus h, the output is c, minus f of x, which is c, over h. Prior to evaluating the limit, we simplified the expression. C minus c is 0. 0 divided by h would be 0, giving me the limit as h goes to 0 of the constant 0, and we know that the limit of constants is just that constant. Therefore, our educated guess based on the graph of a constant function being 0, the derivative being 0, was correct. Okay. Let's look at a couple particular examples. Part A. If f of x is equal to 3, then the first derivative, the derivative of 3 is 0. Remember, 3 is a horizontal line, and this information right here simply tells me that the slope at every single point on the graph is 0. Part B. If the function is negative 4/5, what's the derivative? Well, it would be 0. So f prime is equal to 0. Okay. Back over to here, when I said that the best straight line approximation to a graph, to a horizontal line at any point was the line, let's check that. Let's actually find the equation of a tangent line to a constant function. Let's say I'm looking at the function f of x is equal to negative 2. Find the equation of the tangent line at x is equal to 3. First of all, let's draw a picture so we see what we're looking at here. Okay. What I'm doing is I'm looking at the graph of f of x equals -2, which is a horizontal line where all of the y values are -2. Right, this is f of x is equal to -2. And then I want to find the equation of the tangent line when x is equal to 3. On the x-axis, x equal to 3 would be right here, meaning the point on the graph would be directly below that, right here. Best straight line approximation would be this line right here, and it certainly looks like it overlaps the graph of the original function. So what I want to do is find the equation of that black line. So solution. For the equation of any line, we need to find a sequence of 3 things. What's the point on the line, what's the slope, and what is then the equation? So we put all those 3 things together. All right, the point on the line, which would of course be this point of tangency, is going to have the following. The coordinates are the x value, which is your input, and then comma the function value evaluated at that point. All right, therefore the point of tangency would be 3 comma. If I evaluate the function at 3, well, I look at my function here, f of x is -2, meaning the output is -2 no matter what the input is. This would give me f3 comma -2. All right, that's this point right here. That's the point of tangency. Then let's look at the slope. The slope, and I'll emphasize that it's a tangent line by putting m with the subscript t. The slope of the tangent line is given by the derivative of the function f evaluated at the point 3. So it's the derivative of the function evaluated at this particular x value. Well, as we've been discussing, the derivative of f as a function is 0. And therefore, f prime of 3, if I plug 3 into this, if f prime of x is 0 for every x, then in particular, f prime of 3 is also 0. What I now have is the point of tangency and the slope of the tangent line. Let's now put that together and find the equation of the tangent line. Now there's different forms of equations of lines. The one that we need in this particular case, I've got a point and slope, so we'll use point slope form. As a reminder, point slope form says y minus y1 is m times x minus x1. And I'm going to plug in, this is my x1, this is my y1, this is my m. This gives me y minus -2 equals 0 times x minus 3. The right-hand side becomes y plus 2. The left-hand side I'm multiplying by 0, so that becomes 0. And then if I solve for y, I get y is equal to -2, which is expected, right? This is the equation of the tangent line. This is the equation of this is the original function we started with, which verifies that the tangent line to a horizontal line is the original line itself.